Hi, my name is Ayala. I'm a junior biochemistry major, and I'll be working with Dr. Hanley in the Hanley Virus Lab. The Hanley Lab consists of Dr. Hanley herself, a few postdocs, a graduate student, another undergraduate student, and a few analysts and technicians. The lab focuses on flaviviruses, which are viruses such as yellow fever, dengue, West Nile, and Zika, that are spread by arthropod vectors, mainly mosquitoes. Every year, they infect hundreds of millions of people, resulting in hundreds of thousands of deaths, and pose a major health crisis due to the lack of vaccines and antivirals. Historically, they primarily tended to affect tropical regions, however, recent years have seen their geographic range and incidence increase. To combat these diseases, antivirals have to be developed. One method of doing this is by developing new drugs. However, this can take decades before the drugs are released and approved for use. The other method involves repurposing existing drugs. This means that we use drugs that have already been approved for one disease and test them for any effect on viruses. Since the drugs are already FDA approved, this drastically reduces the amount of time needed before they can be released for use. This is one of the research areas in Dr. Hanley's lab with a specific interest in fluoroquinolones, a family of antibiotics that were thought to have antiviral properties, specifically inoxacin, ciprofloxacin, and difloxacin. Research indicates that these drugs do exhibit an antiviral effect on dengue virus, shown as dengue 4. On the x-axis, we have the concentrations of the fluoroquinolones, and on the y-axis, we have the concentration of virus. We see that as the concentration of fluoroquinolones increases, the dengue virus decreases. Although only dengue 4 is shown, this negative trend is exhibited in the other serotypes of dengue. In a recent experiment run with dengue 4, the virus's passage with each respective drug, the ciprofloxacin, became resistant within 7 passages. One replicate developed a change in position 417 from a glutamic acid to an alanine. The other 2 replicates developed a mutation in amino acid 15 from a valine to a leucine. After 10 passages, the difloxacin passage virus also acquired resistance, with all 3 replicates showing a change in position 417. A result of these mutations was increased stability for the cipro-resistant viruses. Here we see virus degradation as a function of time. By hour 24, we see that the parent virus has already been completely degraded. However, in the cipro-resistant and in the media control, we see that the virus degradation has been significantly reduced. By hour 30, the media control is barely below 50, and the cipro-resistant is above 75%. Here we see the alignment for all 4 serotypes of dengue. At position 15, we see that dengue 1 and dengue 3 have leucines, while dengue 4 and dengue 2 have valines. At position 417, we see that only dengue 4 has a glutamic acid, and 1, 2, and 3 do not. Since the cipro-resistant has a leucine instead of a valine at position 15, my project will focus on position 15 and its effect on stability. We thus hypothesize that position 15 is a key determinant of stability, and that amino acid residues leucine or isoleucine confer greater stability than the residue valine. Thus, we predict that dengue 1 and dengue 3, which have a leucine, will have a higher stability than dengue 2 and dengue 4, which have a valine at that position. My project involves repeating the stability assay for dengue 4 but for a longer time period. I will then repeat the assay for the other stereotypes and compare dengue 1 and 3 with 2 and 4 to see the differences in stability. I will then proceed to substitute valine for an isoleucine and run the assay again and compare to see if variation in the region correlates to stability.